So welcome back friends. So we are looking at understanding the rotation group for dimensions more than 2, okay, and now what it has to do with the spinors and everything which I introduced, essentially we will come to that in a bit more in detail. So to make that connection we need to understand the rotation group in at least more than 2 dimensions. So what we have seen in the last class essentially is that, so for any general rotation groups are essentially orthogonal groups, and for any general n, so where n is the dimension of the rotation group, essentially we can use conditions as follows. Essentially write the general form of the matrix, multiply it with each other and define the number of free parameters, and we derived how many free parameters are there for a general rotation group for a general n. So there are n square parameters of any matrix. Essentially any matrix would have n square parameters, and the orthogonality conditions so orthogonality conditions give you n into n plus 1 by 2 conditions essentially, and so the number of free parameters which satisfy all these conditions will give me n into n minus 1 by 2, okay. So this relation for 2 is equal, for 2 it comes out to be 1, which is nothing but the theta angle essentially, and the group is what we have seen is abelian. Essentially that means that it does not matter how you do the order of rotation. So you can do one rotation and another rotation and then you can do the first rotation first or second rotation first and the first rotation second, even then you get back the same group element. So the group is abelian. That means if you the order of multiplication will not matter for 2 dimensions, for n is equal to 2. Now for n is equal to 3, the number of parameters describing the orthogonal matrix is equal to 3. We have seen it essentially, but this is also understandable because we know that in rotations in 3 dimensions these are nothing but your 3 angles. There are 3 angles. If you remember your classical mechanics, these are your Euler angles essentially, and this r theta and phi, r theta psi and r of theta psi and phi are your 3 angles of rotations which are describing your group elements, the product of this each of them. And what this r and theta are is nothing but rotation in xy plane, a generic rotation in xy plane given by which is a finite rotation, okay. This is a finite rotation. As psi is in yz plane and zx plane, you have cos phi, sin phi and minus sin phi. Now the generators, now if we want to understand what are infinitesimal rotations, that means when theta goes to 0, very small rotations, why does you can do essentially. The thing I will tell you why we need it, and then generators which we derived at the end of the last class essentially was that you can derive these generators as the derivative of the R matrices R of theta divided by derivative with respect to theta as the limit theta goes to 0, okay. There are sometimes sign conventions essentially, okay. Now this is given by this particular matrix which is 3 by 3, which has all other entries 0 except where the sin theta is there, you have 1 minus 1 essentially. Now the same thing you can do for yz plane and zx. So the point is that a generic O3 group element can be described as follows. Now the important point is that when the limit theta goes to 0, there is no rotation. There is also always an identity element in the orthogonal rotation, okay. In the orthogonal group there is always an identity rotation. So you can imagine that you start with no rotation and then do small rotations, and if you do n number of times, you end up with that series ends up being cos theta, sin theta and minus sin theta. Okay, using that idea you can express any group element essentially which is an element of r theta r of theta psi and phi is equivalent to e power I. I'll express what this theta bar times x bar is. Okay, so this theta bar x bar is nothing but e power I. Theta bar is nothing but theta psi phi if you write them as a vector, and x is x theta psi theta phi x, the generators here essentially. Oh, x psi x phi. So that is equivalent to e power I theta times x of theta plus psi times x of psi plus phi times x of phi. So this is the most general group element. Now if you expand this, you can expand this. Okay, you can expand this. I will not go into the details of this. What you will end up, and you can formulate the group axioms essentially, meaning what is called as the algebra of the group essentially. So you end up know why these generators are important is that because if you expand this and do some algebra, you will notice that this should be because if you expand this goes as 1 plus so on, and this is the group element, and now you can impose the conditions what happens and everything. So after doing a little bit of that, you end up with the conditions, because it's a series if you remember, with the condition that x I x j is equal to I epsilon I j k x k. So the generators do not commute but end up giving this kind of relations essentially. Okay, okay. After doing some algebra, after some calculations and imposing some conditions essentially, okay, you can derive this sort of something called commutation relations between the generators. And this commutative relations is nothing but called called group algebra. This is the called as group algebra. I used the word algebra some time ago. So this is the group algebra. That means that you can write commutation relations between generators of infinitesimal notations, and the generators of the infinitesimal notations give you this thing. So the commutator between xi xj, meaning I is equal to theta psi and phi. Okay, I can be this, and epsilon ijk is essentially your Levi-Civita tensor essentially. Okay, Levi-Civita tensor which is becomes one such that epsilon 1 2 3 is equal to plus 1. Okay, with the definition that epsilon 1, 2, 3 is equal to plus 1 essentially. So these generators do not commute with each other, they satisfy some commutation relations. Okay, there are other things also, something called the Bianchi identity which they satisfy, but it is not important for us. But so these commutation relations satisfy this particular condition. Also something called the Bianchi identities. Okay. Okay, Bianchi identity is we will not need it right now essentially, so I will skip it essentially. So this these commutation relations give you tell you everything about the group, essentially, and they set up the group algebra and so on, so essentially. So with this, so what we see is that now in general you can write as XA XB is equal to something called FABC XC. So in general you have for all the groups of this type which start with unity and which can be infinitesimally transformed into some can be thought of in terms of rotations. This is called these are called the Lie groups. For a general Lie group, one has typically a Lie algebra of the type XA XB is equal to I FABC XC for its generators, and these are called something called structure constants of the group. So once we know the structure constants, everything about its algebra, everything about its representations, everything is known essentially. That is the reason why this is a very powerful technique to know all its meaning all its the nature of the group, nature of the Lie group and everything. Okay, good. So we covered n is equal to 3. This is important because so the first part about it essentially is that that the SO3O3 rotations form something called a Lie group, and it has its these are its generators, and the generators satisfy these commutation relations and so on. So okay, good. And other thing I mentioned that these angles theta, psi and phi are compact. Essentially the dimension of these things is compact. That means the domain of these angles for the rotation group comes back to itself 0 to 360 degrees, so is compact. Okay, the dimension of this group angles is compact. So 360 degrees, because 360 degrees is equal to 0 degrees, so it comes back into itself. Such domains, the groups with such domains for the angles, Lie groups with such domains for the angles are called compact Lie groups. compact Lie groups. Now what happens, are there any cases in which these and if they are physically interesting or not, essentially the point is that whether they are such things are physically interesting or not. Okay, yes, meaning you can imagine that instead of rotations, okay, and the rotations will always lead to something like compact, essentially cos theta and sin theta. Now suppose if I replace cos theta and sin theta with hyperbolic angles, say for example cos xi and sin xi or so on, so the domain, okay, is minus infinity to plus infinity of this angle essentially. Okay, now okay, non-compact Lie groups. Now rotations, we know these compact Lie groups are there in nature, we observe them all the time essentially. Now what about non-compact Lie groups? Are there examples? Let us consider an example essentially. Okay, let me consider a rotation, somewhat like a rotation, but it is not actually a rotation, but instead I consider cos xi in 2 dimensions. Let us start with 2 dimensions, sin hyperbolic xi minus sin hyperbolic xi cos xi. Now is this physically relevant somewhere essentially? Now xi has a domain minus infinity to plus infinity because hyperbolic angles are completely defined in such way essentially. Okay, the domain of xi is minus infinity. Now is there any place where this xi appears essentially in nature essentially? So where is the place which xi appears in nature? Okay, where does xi appear in nature? Okay, xi appears in nature in a place which we know very well essentially, which we know actually pretty well. It appears in Lorentz boost. Okay, a Lorentz boost essentially, okay, Lorentz boost is when you have 2 frames essentially S1 and S prime essentially. If one of them is boosted essentially or if this one of them is boosted very far with accelerating, it is transformed into by a Lorentz transformation such that its velocity is boosted essentially with say close to the speed of light, say for example. Okay, in such case, so this is an okay, so what we call it, okay, what we call it as it can be thought of, okay, in other words this can be thought of as if you have some event here and in some event here, this is a boosted frame essentially. In the boosted frame, this can be thought of a rotation in hyperbolic angles. That is the point essentially, that the Lorentz boost, the Lorentz transformation can be thought of as a rotation with hyperbolic angles, not with not with ordinary angles essentially. The Lorentz boost can be thought of, this is known, well known in your relativity class essentially. Okay. Say rotation, this word rotation is not really a good word essentially, okay. Thought of as a rotation in can be hyperbolic angles essentially. So you are writing like the matrix is written in terms like a rotation matrix, but it's not really rotation, it's because it's a hyperbolic angle, and such that this is like a transformation with hyperbolic angles. Essentially the Lorentz boost is a transformation with hyperbolic angles, essentially with the domain minus infinity to plus infinity of xi, essentially, okay, with hyperbolic angle. Say xi is the boost factor, essentially xi is the boost factor, okay. Now you all know what is the xi, essentially is the boost factor, essentially. Now what happens if you have a generic boost, essentially if you have a generic boost. Now this is a non-compact book. Now you have seen that non-compact groups also have implications in physics, essentially, that now you are seeing slightly some connections, okay. In general, now this boost is non-compact because it's in x direction. So this r, okay, one second, let me do the 2 dimensions again, essentially the boost. So if you do a boost in x and t, so you get x prime t prime is equal to cos hyperbolic xi minus sin hyperbolic xi minus sin hyperbolic xi cos hyperbolic xi, okay. So now what does it keep invariant? Essentially it keeps the invariant x square minus t square square root of ds square. It keeps this one invariant depending upon the sign of your metric. So in our case it should be t square minus x square, essentially, yeah. So it keeps this the line element invariant. Now this is in x and y plane, x and t plane, essentially. Now but you can now you can also do the same thing yz, zx, yt and zt. Similarly one can have boosts in yt and zt planes. So if I call them, okay, xi, and if I call this angle as eta, this boost factor, not angle really, so this boost factor as eta, this is as xi, this as eta and this as sigma. So in general you can have a generic boost can be written as a product of when I say generic boost, I mean to say a boost in a generic direction, okay, a boost in a generic direction. It could be a combination of x, y and z in some general, okay. So boost in a generic direction as a product of r of xi, r of eta, r of sigma. R of sigma. Now what we have been doing, okay, we made suddenly significant progress, okay, okay, we made suddenly a lot of progress. First thing we said was, okay, we made several things here essentially that boost form a group, okay. and that is also a continuous Lie group. I haven't shown explicitly, but I already made this statement that boost will form a Lie group. That means what it means, that if I have a boost in xi, then I have a boost xi prime, this is equivalent to a boost which is xi plus xi prime essentially. That is the basic idea. This is equivalent to a boost which is xi and xi plus xi prime. Okay, so the first idea is that what we have seen today is that is boosts form a group and that they form a continuous Lie group. Okay. Secondly, the second idea I introduced was that boosts form non-compact Lie group. Okay. Okay, boosts form non-compact Lie group. That means why it is non-compact? The domain of the boost is minus infinity to plus infinity, because boost can be thought of it's V by C. So when okay, so you can have very large amount of boost essentially, as long as it touches the velocity of light, there is always a boost essentially. So you can always go to the speed of light essentially, where the boost becomes infinity essentially. Okay, the boost becomes infinity. Then so this is the second, boost form non-compact group. Then so this is a major thing. Now what we have seen is that this is a major thing. Okay. Now the second thing, the third thing essentially is that you can have boost in three directions. The boost can be in all the three directions essentially. So you can have it in xy, xt, yt or zt directions. You can have boost in three directions essentially, and a generic boost can be a return similar to rotations as a product of boost in xy, xt, yt and zt direction essentially, and they do not commute. Again they do not commute. So they do not commute. That means what does it mean? That means this is a non-abelian Lie group with corresponding Lie algebra. Fantastic essentially. So today we made a very significant step essentially. Okay, we made a very significant step. So we first understood that the three dimensional rotation group is nothing but O3. It has three generators and the generators form something called a Lie algebra, and in general Lie algebras have always a structure of this particular type, giving you this these commutation relations essentially. Okay, these commutations. And the next significant step we made was that these Lie algebras, if they are the rotation group is always a compact group. Essentially, that means that the endpoints are identified with each other. Essentially, 0 is equal to 360 degrees, so it's always a compact Lie group. Then we ask the question that whether there could be Lie groups which are non-compact, meaning they could be groups which are non-compact, and if they have any relation with the physical world, okay, with the physical world. So we said that okay, instead of taking cos, I take cos hyperbolic angles. Essentially, these are non-compact because hyperbolic angles are not bounded by up and below. Essentially, these functions are not bounded. Essentially, they go from minus infinity to plus infinity. Similarly, you have the domain of the parameter is essentially minus infinity plus. Now then I made the claim that these are nothing but Lorentz boost. Essentially, these seemingly rotation like what do you call non-compact objects rotations or transformations are like Lorentz boost. So Lorentz boost can be thought of as a rotation in hyperbolic angles. So one can have boosts in y. What do they keep intact? They keep the line element intact under rotation. The rotations keep the length of the vector intact, whereas the boosts keep the di s square minus the length of the line element intact essentially. And we said that they can be written in this particular fashion. A generic boost can be written in this particular pattern, and boost. So the main takeaways from today's lecture are that boosts form a group, continuous Lie group, non-compact Lie group, and they are non-abelian. Okay, they are non-abelian. Now, with this background, and we will do some more background essentially, we are now ready to tackle the issue of Lorentz group, and then we will come back to representations, and then how do unitary groups come into this picture, and how do Dirac-Spinors come into this picture essentially. So that is the target for the next few lectures essentially. So I will stop here. Thank you very much, and I hope to see you soon actually. Okay, thank you.